So projectile motion is just something that's being launched or thrown or pushed, all right, under, it doesn't have any power itself. So like a rocket that's blasting off, okay, for a time period while the engine's running, it's not a projectile, okay? But as soon as the engine cuts off and gravity starts to pull it back down to earth, then it's a projectile, okay? So anything that's pulling something back down to earth, and there's no like engine attached or something pushing it, all right, then it's projectile and it behaves in a certain way, okay? So projectiles, a few things that we need to do, I should have said this, examples: throw softball, football, the dart like I showed you guys in the video last week, long jumper, high jumper, even a bullet that's shot, okay, after it takes off from the gun, then it's a projectile because gravity's going to pull it back down, okay? And so projectiles always follow a parabolic path. That's this dashed line right here. Okay, so this is going to be a ball that we're going to be talking about that's rolling off of a table. I should have slid this up. Okay, so a ball that's rolling off the table. This is the parabolic path right here. Okay, to simplify the motion or projectile motion, we're going to break it into horizontal and vertical motion. Okay, so, and that's what it is. It's a combination of moving horizontally and also vertically, like we did with the demo I showed you with the Steelies. Okay, all right. So vertical motion is free fall. So the vertical motion in a projectile is just like dropping it. Okay, and so if you looked, if you saw in the demo that I did, you saw that as time went by, the one that was dropped and the one that was launched horizontally were at the same height all the way down. That's because the difference between them is one has some horizontal velocity attached to it, whereas the other one doesn't have any horizontal velocity attached to it. Okay. All right. So with this diagram, there's a few things. All right. We always start measuring things from right here, from where the projectile motion started, which is right here on the edge of this table, okay? So this ball is rolling off. It has a velocity. It's been pushed or something, all right? And so I want to go through all the horizontal components first, and then I want to start talking about the vertical components, okay? So right here, we have this arrow right here represents the positive x-axis, but it's also a vector, and it's I'm going to label it V sub x. Okay. And it's the initial velocity, but you're going to see in just a little bit that the initial velocity and the final horizontal, okay, let me back up. The initial horizontal velocity and the final horizontal velocity are going to wind up being the same value. Okay. So that's why, just for simplicity, I'm writing V sub x right here. Okay. Because we start measuring right here, this is going to be the start of my horizontal distance that I'm measuring. Okay, so that's going to be the start of that's going to be an initial position, and we're going to call that 0. So this is where we're going to start the tape measure, and we're going to measure horizontally, and we're also going to measure vertically. Okay, and so this is the initial velocity, horizontal, and then we also have x sub 0, x sub o, I should say, the original position, and we're going to call that 0, and we're always going to do that. Okay, so this is going to be 0 meters, and the acceleration, okay, because we've just pushed it and then and we haven't kept pushing it or anything, then that means that the acceleration in the horizontal direction, in the x direction, is equal to 0 meters per second squared. And knowing that these are 0 are going to simplify some of the equations that we're going to use. All right. This distance right here represents how far horizontally this ball will travel. Okay, so it's going to travel a distance vertically and also horizontally. Okay, and so since this is 0 and this is the final position, we can call this entire length x. All right, and that's going to be the horizontal displacement. So let me write that. Okay, so that's going to be how far it travels horizontally. All right. One other thing is, as this lands, okay, this is going to have two components to it. It's coming down at an angle this way, right? And so this, we have a resultant vector that's coming down, all right? But that resultant vector is made up of the horizontal velocity, and that right there is my v sub x. It's the final, but again, I'm going to tell you, these are going to wind up being the same because our acceleration is 0, okay? And I'm going to show you that in just a minute, all right? Okay, so now let's talk about all the vertical pieces, okay? As you saw from the demo, okay, this behaves just identically as if you just dropped it, okay? So if you drop something, then it starts from rest, which means the initial velocity in the y direction is 0 meters per second. So right here, okay, and we have, this is going to be a little bit hard. This is subscripts, okay? So we'd say v sub y, velocity in the y direction, original, okay, is equal to, and because it behaves just like that one we dropped, the initial velocity, the starting velocity in the y direction is 0 meters per second. Because we're measuring from this point right here vertically, that means y sub 0 is going to be 0 meters. And we have acceleration, okay? So a sub y, the acceleration in the y direction, well, because of gravity, the acceleration in the y direction is just g. So we automatically know that one too. That's negative 9.8 meters per second squared. So we don't have acceleration in the horizontal direction, but we do have acceleration in the vertical direction, and it's this negative 9.8. The other thing here is that since this is the origin and this is the positive x-axis, okay, this would be the negative y-axis, okay? So this distance right here that we travel is y, okay? And it's the vertical displacement. All right? And because it's going downwards, okay, so vertical displacement is a vector, and since it's going down, we need to realize we're going downwards, so the direction downwards is negative, because this is 0, all right? So that means this is always gonna be always negative. So this y right here is always negative, okay? All right, so down here at the end, this is gonna have at the very end, it's gonna have a velocity component that's horizontal and also one that is vertical, okay? And this right here is velocity in the y direction, but it's the final one, okay? Over here, it starts at 0, but over here, it's not gonna be 0, all right? So that's all the vertical information that we need. All right, so here's the other part. We have a velocity vector right here coming down, and it represents it coming in and hitting the ground, okay? So this velocity vector we will label it v sub r. For r stands for the resultant vector. Let me slide this up a little bit. And then this angle right here, the small little angle right here, is going to be my angle theta. So from last week's lessons, I know that v sub r we can grab by using the Pythagorean theorem. So this would be the square root of my velocity, my horizontal velocity x squared, plus my final velocity in the y direction. Okay, so v sub y comma f squared. Because I know these two, I can get this angle because I know that tangent of angle theta is equal to the opposite, which is the velocity in the y direction final over the velocity in the x direction, because that's the adjacent leg. And then I could take tan inverse of both sides, and angle theta is exactly tan inverse of the velocity in the y directions final over the velocity in the x direction. Okay, a lot of these subscripts, because we want to use v for velocity, and then we got to say, okay, there's different velocities, right? There's the resultant velocity, and then there's the horizontal velocities and the vertical velocities, okay? All right, so let's turn the page, and I'm going to refer back to these because some of these are zero, and it's going to simplify some of the equations that we're going to use. And I'm also going to explain why is this velocity at the beginning the same as the horizontal velocity at the end, because it will be. Okay. All right, so I'm going to turn the page now. So I'm going to try to do all of my horizontal in blue and all the vertical motion in red so you can tell the difference. All right. So we start the motion at where the motion begins. Okay. So that means x sub 0, okay, or x sub o. I keep saying x sub 0. X sub o, we know from the previous one that x sub o is 0 meters. So we're starting at the initial position 0 meters. So x of o is equal to 0, which means that's 0. So really we can cross this out. All right. It's not going to play a part in our equation. Okay. So really what happens is this equation becomes x, okay, the horizontal distance it travels, okay, is equal to the velocity in the x direction times time. Okay. So what this is saying is the horizontal, the distance traveled horizontally okay, so that's my x, that's the distance it travels horizontally, is equal to the horizontal velocity multiplied by the time. So the time it was moving horizontally, okay? That's what this is saying, okay? This is going to be a really important formula that we use. We're going to use that a lot, okay? Now this one over here, okay? The acceleration in the horizontal direction, okay, is 0. So a of x is equal to 0. There's no acceleration in the horizontal direction. So that means this equation right here, this is going to be 0 times time. So this is going to be gone in our equation. And basically this is why, okay, the velocity in the x direction final is equal to the velocity in the x direction original. Okay, so I should have put a comma right there. Okay, so that means the velocity between the final velocity horizontally and the initial or starting velocity are the same thing throughout. So that's why we come right here and we go, okay, we can just, instead of, there's no difference between the final and the original. So that's why we're just going to write v sub x. Okay, and so v sub x represents the horizontal velocity. All right. Okay, and so what this is saying is the horizontal initial velocity is the same as the horizontal final velocity. Okay, now that one's not going to be that much, it's not as important as this one. This one's going to be used like on almost every single problem. Okay. All right, let's go to the next one. So vertically, okay, we know the starting velocity is 0 and the starting position is also 0 meters, and a sub y is g. Okay, so right here, the initial velocity in the y direction, we know from that diagram and the experiment that I showed you guys, or demo, that v sub y original is equal to 0 meters per second. Okay, so because that's 0, that means this is 0 right here. So that goes away. And so what this gives us is that the final velocity in the y direction is equal to the acceleration in the y direction times time. All right, so what is a sub y? A sub y is acceleration in the vertical direction, and that's just g. That's always going to be g. That's negative 9.8 meters per second squared. All right, so knowing this leads to this simple equation right here. The velocity is equal to the acceleration times time, okay, in the vertical motion. So then right here, y sub o is equal to 0 meters. And I know the velocity in the y direction original is also 0 meters per second. So that means this part is gone. And because this is 0 and I'm multiplying by t, this is going to be 0. So that's gone. And so what this equation simplifies to is that the vertical displacement right here is equal to 1/2 times the acceleration in the y direction times t squared. And once again, a sub y is equal to g, which is equal to negative 9.8 meters per second squared. And then the final equation is using these again. Okay, we know that the initial velocity in the y direction is equal to 0 meters per second. And I also know the initial position. That's where we're starting the measure tape. That would be y sub o is equal to 0 meters. Okay. And because both of these are 0, this is going to be 0. So when I square it, it's still going to be 0. So this is going to be eliminated. This right here minus y sub 0, well, that's 0. So this is going to be eliminated. So basically what this gives us is the final velocity, a different way of getting the final velocity. This is going to get the final velocity by knowing the time and the acceleration. This is going to get the final velocity by knowing the acceleration and the vertical displacement, okay? So this means the velocity in the y direction, f squared, is equal to 2 times the acceleration in the y direction times y, all right? And so again, a sub y is equal to g, which is equal to negative 9.8 meters per second squared. Okay, so we're going to break this up into the horizontal and also the vertical components. Okay, all right, let's go do some problems. So really there's 4 equations that we're going to use. Okay, you know what? And I forgot to do something. All right, I was going to do this. Okay, so this is going to be an equation that we're going to use. This one's one that we're going to use. We're going to use this one a lot. Okay, this one sometimes. Okay, this one not much at all. This third one down here. Okay, but there are really 4 equations that we need to know. Now I will give you these to you on the final. Okay, so you don't need to have them memorized. All right, you just you need to know how to use them. Okay. All right, so now let's go, and what I want to do is I want to write these 4 equations that we could use. So we know x is equal to v sub x times time. That's a horizontal formula we can use for horizontal motion. We also know that the velocity in the y direction final is equal to the acceleration in the y direction times time. We also know that the vertical displacement is equal to 1/2 times the acceleration in the y direction times t squared. And then we also know that the velocity in the y direction final squared is equal to 2 times the acceleration in the y direction times the vertical displacement. Okay, so now we're going to use some of these equations in order to figure this out. Okay, this next problem. So the Forest Hill Bridge near Sacramento rises 220 meters above the North Fork of the American River. So there's this bridge. It's 220 meters above the river. Okay, that's what that says. Okay, suppose you kick a rock horizontally off of the bridge. Okay, off the bridge. The magnitude of the rock's horizontal displacement is 55 meters. So you're going to kick this rock. You're going to, in a specific way, horizontally, so straight across. All right. So let me grab this pin. So here's my rock, and we're going to kick it horizontally, which is going to cause it to come off the bridge and fall, and it's going to fall using this parabolic arch, okay, or parabolic path. All right. Now, I know a few things. So this is where the bridge is. This is where we're measuring, okay? I know that the magnitude of the rock's horizontal displacement is 55.0 meters. That means it travels horizontally 55 meters. So where we kicked it right here off the bridge, when it came off the bridge, right when it came off the bridge, that horizontal distance the rock traveled is 55 meters. Okay. And then what we want to know is that, okay, when we kicked it, we gave it a velocity in the horizontal direction. Okay. And that's actually, I want to find the speed at which the rock was kicked. That's what I want to find here. I want to find V sub X. Now I know one more thing. I know how high up this was. Okay. And that was 220 meters. Now we got to be careful here. Okay. Because what we have is a coordinate axis. And again, this is where we're measuring, okay? This is where we're measuring all of our distances. Now this is going down. So what that means is since this rock is falling and it's going down, this is going to be a negative distance it falls, because right here is 0 and going up is positive, and so going down would be negative. So remember, vertical displacement is a vector, and since we're starting up here and we're going down, this vertical piece right here has to be not 220 meters, but actually negative 220 meters. And the negative just tells you down from where you're starting. So this is where we started. We're going down negative 220 meters. Okay. So now what do we know? Okay, so we don't know V sub X. That's actually what we're trying to find. Okay, and so that's a horizontal piece. So there's 3 pieces to this, right? We do know X because that's the horizontal displacement. We know that's 55 meters. So we know X is equal to 55 meters. But I don't know how long this took to fall and go horizontally 55 meters. So we also don't know T. So that this leads to a problem, right? We have 3 things in this equation. We need 2 of them to solve it. We only have 1 of them. Okay. So we want to end up with this one. So we need a way to come up with our time. Well, we also have this vertical displacement, right? And so this relates the vertical displacement, okay, with the vertical acceleration and time. So I'm going to use this one because I know my y, which is my vertical displacement, is negative 220 meters. Okay, I also know that a sub y is equal to g. So I know that has to be negative 9.8 meters per second squared. And so I need to find time. So the time it takes to drop is the same time it takes to go horizontal. Okay, so these 2 times are actually the same time. So once we find this one, we're going to be able to plug it in here, and now we'll have 2 of these, and we'll be able to find the velocity in the x direction. That's the whole idea behind it. Okay, so right here, I know y is equal to 1/2 times a sub y times t squared. So I know my y is this negative 220 meters. So negative 220 meters is equal to 1/2 times my acceleration in the y direction, which is negative 9.8 meters per second squared times t squared. So I want to get rid of this fraction. So this is multiplying by 1/2. If I multiply by the reciprocal of this, which is 2/1 or just 2, if I do that, that's going to make a 1 right here. So I'm going to multiply both sides by 2. So the left side becomes 2 times negative 220 meters is equal to, and then 2 times 1/2, well, that's just 1. So this becomes just negative 9.8 meters per second squared times time squared. And then I want to get the t squared by itself, and then I'm going to get t by itself. Okay, so I'm multiplying the t squared by negative 9.8, so I'm going to divide by that. So this is 2 times negative 220 meters divided by negative 9.8 meters per second squared. That's equal to t squared. I'm going to square root both sides. So t is equal to the square root of 2 times negative 220 meters divided by negative 9.8 meters per second squared. All right, now, when I square root a square like this, you get two answers. You get the positive and the negative, okay? And we talk about that in math classes, all right? Now, because time is positive, the time has to be positive. So we're just going to give the positive answer. Because of the situation we're in, it has to be positive, okay? So this turns out to be positive, okay, square root of 2 times negative 220 meters divided by negative 9.8 meters per second squared, okay? So I'm going to grab my calculator and I'm going to put that in, okay? So in my calculator, we want to make sure we're in degree mode, okay? Whatever calculator, whether you're using Desmos or not, okay? We want to go square root, and then I want to get a fraction, and in the numerator, I want to type 2 times negative 220, and in the denominator, negative 9.8, and press enter, and we get a time of 6.7. Okay? You want to go 2 decimal places because our final answer, we're only going to round to 1 decimal place, okay? All right, so here's 6.7 seconds, okay? That means up here, this time, okay, we figured out this is 6.7 seconds, which means this time right here is also 6.7 seconds. And now I can use this equation to solve and find my velocity, okay? So I know that x is equal to v sub x times time. And so I know my x is 55 meters and is equal to v sub x times, and I know my time now is 6.7 seconds. And so I'm going to divide to get v sub x by itself. I'm going to divide both sides by 6.7, and I get 55 meters divided by 6.7 seconds is equal to v sub x. And so my v sub x, that's my horizontal velocity, okay, that's the speed at which I kick the rock at, okay, is 55 divided by 6.7. And we get 8.2, rounding to 1 decimal place, we get 8.2 meters per second, okay? So that means the rock was kicked at 8.2 meters per second. Okay, and that's the speed at which it was kicked. All right. So hopefully that's starting to make sense. Okay, hopefully maybe you're watching this for the second time. Okay, and this is helping you out. All right. So again, I want to write the 4 equations. It's x is equal to v sub x times time. That's the only horizontal equation that we can use. All right. And then we also know that, sorry, I went blank. V sub y comma f is equal to the acceleration in the y direction times time. And we know the vertical displacement is also equal to 1/2 times the acceleration in the y direction times t squared. And then we also know that the velocity in the y direction final squared is equal to 2 times the acceleration in the y direction times the vertical displacement. Okay, so here we go. A CAL FIRE rescue plane drops a package of emergency rations to stranded party of firefighters. So if the plane is traveling horizontally at 30 meters per second at a height of 200 meters above the ground. Okay, so there's only 2 pieces of information in this, right? We have a plane, so I'm going to draw my little plane, okay, my CAL FIRE plane. So something like this. Okay, and that's the wing, all right? And so what it's going to do is it has a package and it's going to release it and it's going to drop. And as it drops, it's going to continue to go forward and also fall to the ground. Okay, so it's going to take on this parabolic path. Okay, something like this, and crash into the ground. Okay. Now, what do I know? We're starting the measurement. We're starting our coordinate axis right here. So that's going to be the origin. So that's going to be my initial position. So my vertical position is going to be 0. My horizontal position is also going to be 0. I know I'm going horizontally with a velocity v sub x right here, which is 30 meters per second. Okay. I also know that the height is 200 meters above the ground. So this plane from here to here, okay, this vertical distance right here is 220 meters. But because we're calling this is where we're starting the tape measure and we're going downwards, this isn't 200, it's actually negative 200 meters. So all we have is this horizontal velocity and we have the vertical displacement, and that's all we have. And so the question A is, what is the package's horizontal displacement before it lands? Okay, so how far does this package travel horizontally? That's the question that's being asked. So that'd be from here to here, and that would be my x. Okay, and that one's always going to be positive. Okay, so this one's always going to be negative, and this one's always going to be positive. Okay, so then what that means is that we know v sub x is equal to the 30 meters per second because that's my horizontal velocity. I'm trying to find x. That's what I'm trying to find. What I don't have in this equation is time, right? I don't have t. Okay, so how could I get t? Well, once again, since I know this vertical displacement, my y is negative 200, and I know a sub y, I'm going to be able to use this equation and solve for t and get the time it took to fall to the ground, which is also the time it took to go horizontal. Okay. All right, so then because of this, I know my y is equal to negative 200 meters. I know my a sub y is equal to g, which is equal to negative 9.8 meters per second squared. And then we need to find what t is, because once I find this t, I will have it and I can put it right here and then solve for the horizontal displacement. Okay. So once again, I'm going to use y is equal to, like I said, this one's going to be an important one, and this one's going to be an important one a lot of times. Okay, so y is equal to 1/2 times negative 9.8 meters per second squared. Hey, oh, hold on. I'm writing the wrong thing. I was going to write the equation. Let me restart this. Okay, so back to this. We have y is equal to 1/2 times a sub y times t squared. And now I'm going to put everything in. So my y is negative 200 meters is equal to 1/2 times a sub y, which is negative 9.8 meters per second squared, times t squared. So I'm going to multiply both sides by 2. So that'd be 2 times negative 200 meters. And that's going to cancel this out. And I'm going to have equal to negative 9.8 meters per second squared times t squared. And so I'm going to divide both sides by this negative 9.8. So 2 times negative 200 meters divided by negative 9.8 meters per second squared is equal to t squared. Okay? So the next thing we need to do is square root both sides. So I wind up with t equaling the square root of 2 times negative 200 meters divided by negative 9.8 meters per second squared. And so I'm going to put that into my calculator and I'll have my time. Okay. So it's time to charge my calculator. Okay. So the square root, and I need a fraction. So then 2 times negative 200 divided by negative 9.8. And you wind up with 6.39. So 6.39 seconds. So that's how long it took to drop, okay, from 200 meters above. It took 6.39 seconds to hit the ground, okay? So this is 6.39 seconds. I said the wrong thing. That makes this one also 6.39 seconds, all right? And now because I have the time for this one and the horizontal velocity, I can figure out, all right, my horizontal displacement here, okay? So I know that x is equal to the velocity in the horizontal direction times time. So that means x is equal to 30 meters per second times 6.39 seconds. And so my horizontal velocity would be 30 times 6.39, and you get 191.7 meters. Okay, so 191.7 meters. Okay, so the package's horizontal displacement, this is the answer for A. Okay, the package's horizontal displacement is 191.7 meters. All right, that's part A. Okay, now for part B, we want to find the velocity of the package just before it hits the ground. Okay, so just before it hits the ground, it has a velocity at an angle. Okay, so that means that's a vector. Okay, so that means we have to figure out what the horizontal component is. Well, we know the horizontal component is the same as the initial velocity of 30 meters per second. So this package is going horizontally continuously the whole time, 30 meters per second, okay? So this is 30 meters per second. And then I also know there's a vertical component here. So I'm gonna go straight down, okay? It starts out at 0, but down here, it's gonna have velocity because of acceleration, okay? So this is the velocity in the y direction final. That's the final velocity in the y direction, okay? And we don't have that. It wasn't given to us, all right? But we can figure it out, all right? Because we have this that deals with the final velocity in the y direction, and we also have this one. We're gonna wind up using this one, okay? Because it's just a little bit easier because guess what? We have the time and we have the acceleration, okay? So what we're gonna do is we know we gotta find this vector. This is, and I'm not quite lined up, I know that, okay? But this is to get you the understanding of what's happening. This vector, the amount it's going to go into the ground at this angle, okay, that's my velocity of the package, okay? That's the direction of movement. So we're actually not seeing it go horizontal, and we're not seeing it going vertical. We're seeing the combination of the two, and that's why it looks like this, okay? And that's my resultant vector, okay? And then my angle would be this angle right here, this angle theta, okay? So what does that mean? Okay, we know, okay, for part B, we know V sub x is 30 meters per second. And I also know, okay, I need to find V sub y, the velocity in the y direction, the final velocity in that direction, okay? So I can get that because, let me show you. That's what I'm trying to find. I know that the acceleration in the y direction is g, which is negative 9.8 meters per second squared. And I also know the time because this took 6.39 seconds. So I'm getting this from part A. Okay, so 6.39 seconds. So I know, all right, that v sub y comma f, the final velocity in the y direction, is equal to the acceleration in the y direction, okay? So that'd be a sub y times time, okay? So v sub y of f is equal to negative 9.8 meters per second squared times t, which is the 6.39 seconds. So negative 9.8 times 6.39 And that equals negative 62.62. So the final velocity in the y direction is, I got to get it back, negative 62.62 meters per second. Okay, and that should make sense because we're going in the negative direction, right? The velocity is headed downwards. Okay, that's why this is coming out to be negative. Okay, so now what we need to do is we need to find the magnitude of the vector. So that'd be the velocity resultant is equal to the square root. We're just using Pythagorean theorem. So 30 meters per second squared plus negative 62.62 meters per second squared. And we put that into our calculator. So square root of 30 squared plus negative 62.62 squared. And we get 69.44, right? 69.4. 69.4 meters per second. So that's the velocity of it going in the direction it's traveling, okay? That's the velocity at which it's hitting the ground. So it's not hitting the ground at negative 62.62 or 30. It's actually that velocity, okay? And now we have to find the tangent of theta. And tan theta, because we've got to find the direction, okay? Tan theta is equal to the opposite leg, which is this velocity in the y direction final, which is negative 62.62 meters per second. And we're going to divide that by the adjacent leg, which is 30 meters per second. Okay, so I'm going to take tan inverse of both sides, and angle theta is equal to tan inverse of negative 62.62 divided by 30. And so my angle theta, when I put that into my calculator, okay, make sure you don't press tangent. It's actually tan inverse, okay, and negative 62.62 over 30. And we're almost done. And so that gives you an angle of negative 64.4 degrees. And make sure you're in degree mode, okay, when you do that. So look at your calculator or Desmos and make sure you see the word degree or DEG, okay? All right, so that means this angle, and that makes sense because this is a negative angle because we're rotating clockwise, right? Okay, so that means the velocity of the package is, okay, and we'd say 69.4 meters per second. And since this is negative, we're rotating below the horizontal. So we could just say negative 64.4 degrees, or we could also say 64.4 degrees below the horizontal. Okay, so you're going to see that, okay, where you say below. Now, something else, okay, if you extend this velocity vector out this way, okay, along with the horizontal, if you remember from math 2, okay, in geometry, this angle right here and this angle are vertical angles. So this angle is 64. So this makes more sense to me, okay? We can say it this way, where it's below the horizontal, but I want to know what the angle with the ground it's making, right? And so it's making an angle with the ground when it's going into the ground. It's going in an angle of 64.4 degrees. Okay, so that doesn't have to do with direction. That's just size. This angle is 64.4 degrees. So when it's coming in at an angle to the ground of 64.4 degrees, and it's coming in at a speed of 69.4 meters per second. Okay, when it hits the ground. All right, guys. So that's projectiles launched horizontally, okay? And then, so Thursday and Friday, what we're going to do is we're going to do projectiles launched at an angle, okay? And so we'll take my projectile launcher that you saw, and we'll launch some steelies, all right?